this, believe it or not, this particular set of notes is, this particular example is based in something that actually happened, a lawsuit that happened, I don't know, about 10-ish years ago, where a group of people out of Chicago were pretty upset with, they went to Subway, they bought a foot-long sub, and the average of their subs was less than 12 inches. And they were like, I'm paying for a foot long, you're advertising it to be a foot long, something isn't right. So what they did is somebody was mad. And then what happened is they said, well, we know that not every sub is going to be exactly 12 inches long. So they went out and they took a sample of subs and they measured them. Okay? So everything on here, guys, the numbers I made up. Okay? The lawsuit I did not. And it ended up being settled outside of court because Subway has deep pockets, which is why people did this, right? Okay? And so here we go. You guys ready to work on this? Okay. All right. So the first thing we're going to do is write our null and alternative hypotheses. This is no different than the null and alternative hypotheses that we wrote when these were about P. But now, we're not talking about what percent of our population has something going on. We're talking about what mean. All right? So, in theory, we believe that the true mean of the subs is supposed to be 12. All right? And what happened is we have this sample that's making us think, something ain't right. And in fact, what does our sample lead us to believe? Is the mean bigger than 12 or less than 12? Less than 12. And that's the whole point. People are mad because they're advertising that they're going to be 12 inches long and people are getting less than what they said that they were advertising. Hey, Felix, can you shut that door? Because that beep is going to kill me all day. Apparently during the basketball game, somebody messed with the elevator, and that's the alert that the elevator is broken. Yeah. Okay. Now, a reminder for type 1 and type 2 errors. Type 1 is when we conclude HA even though H0 is true. And so let's go ahead and say we're this group that's debating whether or not to bring the lawsuit against Subway. Is everybody with me? So what would that mean for us? If I conclude HA even though HO is true.
You say that the subs are less than 12 when they are in actuality 12.
We conclude the subs are less than a foot long. Even though they are a foot long. All right, and what would a consequence to that be? We're going to bring on a lawsuit we'll probably lose. All right? So what would that be in this setting?
Would type 2 conclude that the subs are a foot long and they're not?
So we never conclude the null hypothesis, so we're going to fail to conclude the subs are short. Even though they are. Okay, and the consequence to that would be?
You don't get a foot long.
Say that again?
You don't get your whole foot long.
You don't get your money's worth.
Well, so like the idea, so in this particular case, where I want to write these from the perspective of the group that's deciding whether or not to bring a lawsuit against Subway. Okay, so what would they would just not bring up the suit, right? If their sample gave them like, hey, you don't have enough evidence to say these are less than a foot long, they're just not going to sue. So between the two consequences here, bringing up a losing lawsuit versus just not having a lawsuit, which one do you think is more serious in this case?
Bring on a losing lawsuit.
Type 1 in this case is more serious. Period. End of sentence. So we want to use low alpha. So a reminder, alpha is equal to the probability of a type 1 error. So when type 1 is more serious, you want to use a lower value for alpha. When type 2 is more serious, that's when you might want to use a higher value for alpha, like 10% instead of 1%. Okay? All right, now let's go up and say, like, write down some of the important pieces of information. All right, so what they did is they took a sample of 50 subs. So we have in our sample 50 and found that the mean lengths of the subs in the sample, so in this case that X bar is 11.72. Okay? And that the S, the standard deviation of my sample, is 1.43. Now, a reminder, when we run a test, we assume the null is true. So, start thinking of all those possible sample means. Will the shape be approximately normal in this case?
Yes.
Because
It's greater than 30.
my sample size,
Yes.
50, is in fact greater than or equal to 30, so the shape will be approximately normal. I agree. All right. What about the center? If the null hypothesis is true. Remember, let's go back up to our null. What would the mean of the X bars be if the population mean is 12? The mean of the X bars would also be 12. Okay? Now, for the standard deviation of those X bars, we normally do sigma over the square root of n. Okay, that's what we've been doing so far. Except for when we don't know sigma, we have to use s. Is everybody with me? So if I plug that s in, I do 1.43 divided by the square root of 50. So I just use s instead of sigma. Is everybody okay? That's what we just did. All right. And you guys have calculators and are smarter than me. Point 20223. I'm just going to do that. 0.202. Is everybody good? All right. Now, our statistic, what we got from our sample, is that the mean is 11.72. Okay? That's what we think the mean is. Now, because we had to use S instead of sigma, so like before our test statistic, we calculated a Z. We did p hat minus the null hypothesis divided by that standard deviation. We're still going to do that, but we have to use T instead of Z. Because S is a crappy estimator of sigma. But the how we do it is identical. Okay? So you're going to get your T by doing X bar minus your null hypothesis, 12, divided by the standard deviation, which in this case is the 0.202. Kind of drew some arrows as to where each piece of that came from. Okay? So, and I'll just write a little formula here. T is equal to X bar minus the null hypothesis, whatever that is, divided by the standard deviation of the X bars. Okay? And then, Abby, I just see that you're typing that out. Can you help me out here? That sounds about right.
Can you zoom back out to the one you said again?
Is this okay?
Is for the T formula, is that the E or the?
It's the mean that stated within the null hypothesis. So mu 0, that subscript 0, is just the mean of the null hypothesis. Okay? All right. From here, we got to draw a picture of a T-graph. T-graphs look like this. We drew T-graphs last week too. We're just going to use it differently this time, okay? The center is 0. And remember, we don't write out the standard deviation for T's. We write out the degrees of freedom, okay? What are my degrees of freedom here?
Would be 49.
49. And guys, our T value was negative 1.39. And I just got that from our answer right here. And we're going to the left of that value. Now, before we used last time we used the T-graphs, we used inverse T because we knew the area, we didn't know the, we knew the area, we didn't know the boundaries. Now I know the boundaries, I'm trying to figure out the area. Okay? So go back and hit second vars again. Open up that. And when you hit second vars, do you see anything that might, it's not normal CDF because we don't know the standard deviation, but do you see anything that helps? Well, TCDF is what we're going to use here. So you have a TCDF. All right. And then for this one, and when you hit TCDF, it's going to ask you for a lower and upper and degrees of freedom, right? What's my lower, looking at this graph, guys, what's my lower going to be? Negative a gajillion. What's my upper going to be?
Negative 1.39.
Negative 1.39. And then my degrees of freedom is?
49.
49. What are we getting?
0.085.
0.0. So we said our alpha, we don't want to make a type 1 error. We want a low alpha. Okay, so remember, guys, can Joy smell Parkinson's? Why were you guys convinced that Joy could smell Parkinson's?
Probability was extremely high, or was extremely low.
The probability she was just guessing was tiny. It was a low probability. Is everybody with me? So since the sample was unlikely, we rejected that null and concluded the alternative. Is my sample here unlikely? That's what this p-value tells us. Is this an unlikely sample? If I use 0.01 as my standard of unlikely, it's I wouldn't call it likely either. But are we comfortable with the phrase reasonably likely? So since our sample is reasonably likely, and by my definition of that, guys, is that 0.085 is greater than 0.01. Okay? We cannot rule out the null hypothesis. Pretend I know how to spell rule. Therefore, we can't conclude anything. What are you guys thinking so far? Is this crazy? It's okay. All right. Why don't you guys go ahead and write down what you think the hypotheses would be for this? right, so a reminder, when you write your hypotheses, they are about the population, not the sample, okay? So this is saying, if we want to know, does Ms. Meister's students, this number is my sample, okay? So it's not my hypothesis. My hypothesis is, does the sample match the national thing, okay? So this is going to be 71.4 beats per minute. This is not 68.5. The question becomes, does the 68.5 allow us to say that y'all have a lower pulse rate than the national average? That's the question here. Do you guys see what I'm saying? Okay. Type 1. Thoughts?
That would be that we conclude that, conclude that we do have a lower, what's it called, pulse rate than the average pulse rate of US adults, even though the pulse rate is the same, or the pulse rate is lower.
Type 2?
We failed to conclude that Ms. Meister's students have a lower heart rate.
So if I just say that, I haven't really described an error. So you just need to add something like, even though they do. So it's about mentioning what is actually true versus and how that's different than what we conclude. Is one of these more serious than the other, do you think?
Not really.
Not really. So I'm going to use alpha equals 0.05. These are equally bad outcomes. Okay. All right. Shape, center, spread. What do you think? Let's see, we have, if I go up here, we have x bar equals 68.5. S equals 9.54. N equals 75. Sweet. All right, so talk to me about the shape.
Has 75 is greater than 30.
Perfect. Okay. center. Remember, as we do this, describe this sampling distribution, those X bars, all those different possible samples, we're assuming that the null hypothesis is true. So if the null hypothesis is true, 71.4. All right, cool. And the standard deviation of those X bars is going to be calculated by doing the sample standard deviation divided by the square root of my sample size. And I'm not smart.
You're at 1.10.
What'd you get?
1.10.
1.10?
Yes.
Right on. So we have my statistic will be the X bar. My test statistic is going to be T. We're going to calculate that by doing that 68.5 X bar minus 71.4 divided by 1.10. And again, guys, I really am trying to work on color coding so you can see where each piece comes from, because I recognize there's a lot coming from different places. And I'm just going to sit back and sip on my coffee while you guys engage with that.
Negative 2.63 repeating.
Okay? Let me draw a picture. What is our degrees of freedom, y'all?
74.
74. All right, negative 2.63 repeatings over here to the left. A reminder, we put this into TCDF. Okay, because this is T's. Is this feeling okay? And what's my p-value?
0.0052.
That's a pretty tiny p-value. I'm going to call that less than 0.05. Okay. So now we have to make a decision. Does that p-value suggest we can rule out the null hypothesis or fail to rule out the null hypothesis?
We can rule it.
We can, because our sample is so unlikely. Since our sample is unlikely, we can rule out age 0 and therefore conclude Meister's classes have a lower pulse rate than the national average.
This doesn't have to do with the problem per se, but what if the heart rates are just lower while we're in your class? What if they increase when we're in other places?
Interesting question.
Then everything changes.
That would imply Miss Meister is a Zen
Calming
emetter.
force.
Yes, yeah, because most people walk into math class and feel less stressed, for sure.
Maybe this one.
I would venture that it's possible your pulse rates would be different than seventh periods due to the time of the day, especially if any of you guys are caffeine drinkers in the morning. I know that my pulse rate is highest in the morning because I,
I heard
crash
it
my
was 40
caffeine.
ounces